Greetings, friends. Welcome to our lesson on using genetic algorithms to optimize the design of a supersonic aircraft wing. Today, we are going to explore how advanced optimization techniques can significantly impact aerospace engineering, particularly in the design and efficiency of aircraft at supersonic speeds. Supersonic aircraft operate in a regime where the flow of air around the structure moves faster than the speed of sound. At this speed, aerodynamic efficiency becomes important due to increased air resistance and thermal stresses. The design of the aircraft wing is important because it directly influences the aircraft's lift, drag, and overall stability. Optimization in this context means finding the wing design that maximizes lift while minimizing drag, considering the constraints imposed by supersonic flight dynamics. This involves a complex trade-off between different aerodynamics properties which often conflict, such as lift versus drag and weight versus strength. Genetic algorithms are a type of optimization algorithm inspired by the process of natural selection. They simulate the process of evaluation by creating a population of individuals, each representing a potential solution to an optimization problem. These individuals evolve over generations based on their fitness, which in our case relates to how well they meet our design objectives. And genetic algorithms are particularly useful for problems where the solution space is vast and not well understood, making traditional methods cumbersome or infeasible. We use genetic algorithms for wing design by defining genes, the parameters defining the wing, such as span, aspect ratio, and sweep angle. Fitness function, a function evaluating how well given wing design meets or criteria, and evolutionary process. Through selection, crossover, and mutation, we evolve our wing designs to optimize performance. And let's look at the code. All right. First, we import random numpy, then deep. Deep is for genetic algorithms. And here we have a ensure bounds function. This function ensures that each wing parameters remains within realistic and safe boundaries. It iterates over each parameter of the wing, checking if it lies within the allowed range specified by load and up. If a parameter falls outside this range, it is clipped to the nearest boundary. This prevents the genetic algorithm from exploring non-viable solutions. And here we have an aerodynamic function. It's computed as a function of the span aspect ratio and the cosine of the sweep angle. The formula encapsulates how these parameters theoretically affect the lift a wing generates, adjusting for the sweep's impact on the effective wing area. The drag is inversely related to lift, emphasizing that improving lift often comes at the cost of increased drag. The second term adds a penalty based on the wing sweep, representing additional drag induced by wing geometry at supersonic speeds. And here we have an evaluation function. This function evaluates a potential solution by calculating its drag and lift. And the IND tuple, representing an individual in the population, contains the design parameters span, aspect ratio, and sweep. These parameters are passed to the aerodynamics function, which returns the lift and drag associated with those parameters. The function returns a tuple. Here, drag is minimized and lift is maximized, and this setup fits the genetic algorithm's requirement where fitness value need to be minimized. And here we have a mutation function. To introduce variability into the population by randomly altering the genes of individual, which helps in exploring a wider solution space. And it iterates through each gene of the individual with a 20% change. It modifies the gene using a Gaussian distribution centered at 0 with a standard deviation of 3. This introduces significant changes, which is key to escaping local optima. After mutation, it calls ensure underscore bounds to make sure the mutated values still lie within the specified limits, preventing the algorithm from considering unrealistic designs. And here we have a crossover function, and we call it mate. To combine the genetic information of two parent solutions to generate new offspring, potentially inheriting the best traits from both parents. CX blend, a deep crossover function, performs blending crossover which creates offspring by linearly combining the genes of the parents based on a blending ratio. And after crossover, ensure underscore bound is applied to both offspring to ensure that the resulting design parameters do not exceed realistic physical constraints. And this process helps maintain genetic diversity within the population and enables the algorithm to explore new areas of the solution space effectively. Uh, and here, uh, creating the fitness and individual structures. First, fitness mean it defines a fitness evaluation strategy that aims to minimize the objectives indicated by the weights, and it's minus 1 and minus 1. In this context, both drag and lift are considered, where drag is to be minimized and lift is to be maximized. And individual, uh, it is represent a possible solution in the population is defined as a list of parameters which are the design parameters of the wing. Each individual is associated with the fitness mean class, allowing it to be evaluated for its fitness in the context of minimizing the objectives. And here, setting up the toolbox. First, toolbox, act as a container for various genetic operations. It allows for the registration of methods that generate the attributes of individuals, create individuals and populations, and perform genetic operations like mutation and crossover. And secondly, I hope you can see uh, ether underscore span generates the wingspan attribute using a uniform random distribution between 20 and 70 meters. This range is chosen based on realistic engineering considerations and the need to explore a wide variety of designs. And here, at underscore aspect ratio, it generates the aspect ratio using a uniform distribution between 10 and 20, allowing for exploration of thin and wide wings. And here, at underscore sweep, it generates the sweep angle of the wing between 10 and 25 degrees, facilitating the study of various aerodynamic efficiencies and stabilities. And here we initialize individuals and populations. For individual, is configured to initialize an individual by cycling through the registered attribute functions. This means each individual will be created by drawing once from each attribute function, and a population defined to create a list of individuals using tools.unit repeat. It repeatedly initialize individuals to form a complete population, enabling the exploration of a multiple design configuration simultaneously. And then we have a genetic operations. First, evaluate here. Links to the evaluate function that assesses the fitness of an individual based on its design parameters. And mate uses the mate function to perform crossover between pairs of individuals, potentially combining their attributes to produce superior offspring. And mutate applies the mutate function to introduce random modifications to individuals, aiding in diversity and exploration of the solution space. And finally, select uh, implements tournament selection within a tournament size of 3. This method pits a subset of the population against each other to select the best out of a small group, promoting competition and survival of the fittest. And here we have a main function. Let's start. First, population line. It initializes the population with 100 individuals. Each individual is generated based on the definitions provided earlier in the toolbox. And Hall of Fame, it maintains the best ever individual found during the evaluation. And statistics, it collects and computes statistics about the fitness scores across the population during the simulation, and it's set up to track the average, standard deviation, minimum and maximum of fitness values, helping to monitor the algorithm's performance over generations. And generational cycle. Okay. The algorithms runs for 50 generations. Each generation begins by selecting individuals from the current population to create offspring. The selection is probabilistic and based on fitness, guided by the toolbox.select method, which has been configured to use tournament selection. And offspring creation. The offspring are exact copies of selected individuals but are then subject to crossover and mutation. The toolbox.clone methods ensures that we modify only copies of individuals, preserving the original population. And crossover, uh, for each consecutive pair of offspring, crossover is performed with a probability of 0.5. If the crossover occurs, the fitness values of the resulting children are deleted to signify that they need re-evaluation. And mutation and fitness re-evaluation. Let's look at this. Mutation. Each offspring has a 20% chance of undergoing mutation, which modifies the individual's genes. After mutation, the fitness value is also deleted to indicate that it needs to be recalculated. And fitness re-evaluation. After mutation and crossover, only individual in the offspring without valid fitness must be re-evaluated. This ensures that all fitness values are up to date before the next generation. And updating population and recording statistics part. Uh, population replacements first. The entire population is replaced by the offspring. This generational replacement means each cycle produces potential better fit individuals, gradually improving the populations. And Hall of Fame updates the Hall of Fame with the current population, ensuring that the best individuals found in all generations is retained. And statistic compilation and output finally. After after updating the population and the Hall of Fame, statistics are compiled for the current populations and printed. This provides a snapshot of the evolutionary progress, helping to visualize improvements or identify potential stagnation. And finally, we printing the solutions. First, best individual. After completing all generations, the best individual, the one with the highest fitness across all generations, is retrieved from the Hall of Fame. This individual represents the optimal design parameters found by the genetic algorithm. And fitness display. Secondly, the fitness values of the best individual are printed in this context since the fitness includes both drag and lift. These values give a direct indication of aerodynamic efficiency of wing designs. And retrieving and using design parameters. Parameter extraction. To optimal span aspect ratio and sweep are extracted from the best individuals. aerodynamic calculation. These parameters are then passed to the aerodynamics function to calculate the lift and drag for the final optimized design. This step is important as it translates the abstract parameter values into concrete, understable aerodynamic properties. Presenting the optimized wing configuration display. The optimized wing dimensions and angles are displayed in a human-readable format, providing clear and immediate insights into the design characteristic of the optimized wing. And lift and drag display. The calculated lift and drag are represented, summarizing the aerodynamic performance of the wing. These values help in evaluating the practical viability of the design in real-world applications. And lastly, main execution control. This is a Python convention used to ensure that the main function, which encapsulates the executions of the genetic algorithm, is called only when the script is run directly. And it calls the main function, which initiates the entire process of population initialization, evaluationary operations, and final results presentations. And let's look at the outputs. Each line provides a snapshot of the genetic algorithm's population at the end of a generations, and it includes the average fitness of the population. A more negative number indicates that the population is collectively achieving lower drag and higher lift. And standard deviation shows the variability in fitness within the population. Here's okay. Again, shows the variability in the fitness within the population. A higher standard deviation indicates a wider spread in the population's fitness, suggesting greater diversity. And minimum, the best fitness score achieved by any individual in the population during that generation. This is a primary figure of interest as it shows the closest approach to the optimal design. And maximum, the worst fitness score in the population. It helps understand the range of the solutions being explored. And this is a statistic table. Let's look at the real output. First, best individual. It displays the parameters of the best performing individual found during the entire run of the algorithms. This includes span 29.07 meters, aspect ratio 90.65, and sweep 12.67 degrees. These values represent the dimensions and geometry of the wing that were found to most effectively minimize drag and maximize lift under the given simulation parameters. And fitness of the best individual. It shows the fitness value of the best individual, which includes a value of 1.15965 blah blah blah, which appears to be a composite score reflecting both objectives. The exact interpretation will depend on how the fitness function is structured to combine these metrics. And output line span confirms that span as 29.07 meters, which suggests a balance between structural integrity and aerodynamic performance. And aspect ratio at 19.65, this is quite high, indicating a long thin wing, which is typical for high-speed aircraft to minimize drag. And sweep 12.67 degrees of sweep is relatively moderate, optimizing the airflow and shock waves at supersonic speeds. And lift here 191.74, indicating the wing's effectiveness at generating necessary upward force at speed. And final drag 1.16, impressively low, reflecting efficient aerodynamics that would benefit supersonic flight by reducing fuel consumption and increasing speed. And it was a long project, and we came the ends. See you in the next project.